Real numbers. Introduction. We already know about various types of numbers such as natural numbers, whole numbers, integers, rational numbers. We also learned how to represent them on number line. Let us recall them in short. Natural numbers. All the counting numbers 1, 2, 3 and so on are called natural numbers. They are denoted by letter n and represented as n equals to 1, 2, 3, 4 and so on. Whole numbers. Set of all natural numbers and 0 are called as whole numbers. They are denoted by letter W and represented as W equals to 0, 1, 2, 3 and so on. Number line representation of whole numbers are as follows. Integers. An integer is a number that has no fractional part and no digits after the decimal point. An integer can be positive, negative or 0. Integers are denoted by letter Z and represented by Z equals to -3, -2, -1, 0, 1, 2, 3 and so on. Integers are represented on number line as follows. Rational numbers. A number that can be expressed in the form of P by Q, where P, Q belongs to Z, that is integers, and Q is not equal to 0, is known as rational number. Collection of rational numbers are denoted by Q. Q equals to -1 by 4, 3 by 7, -13 by 17, 5 by 3, -69 by 1, 22 by 7. Irrational numbers. A number that cannot be expressed in the form of P by Q, where P, Q belongs to Z, that is integers, and Q is not equal to 0, is known as irrational numbers. Collection of irrational numbers are denoted by Q bar. The square root of any prime number is irrational. There are infinite irrational numbers between two rational numbers. Activity. Consider the following numbers: 7, 100, 9, 11, -3, 0, -1 by 4, 5, 1, 3 by 7, -1, 0.12, -13 by 17, 13.2, 2, 2, so on, 19, -5 by 3, 213 by 4, -69 by 1, 22 by 7, 5.6 bar. John and Sneha want to label the above numbers and put them in the bags they belong to. Some of the numbers are there in their respective bags. Natural numbers, whole numbers, integers, rational numbers. Bag N contains natural numbers, bag W contains whole numbers, bag Z contains integers, bag Q contains rational numbers. 7, 100, natural numbers, 0, 7, 100, whole numbers, 0, 7, -3, 100, integers 0, 7, 100, minus 3, 3 by 7, rational numbers. Now, pick up rest of the numbers and put them into the bags which they belong. If one number can go in more than one bag, then copy the number and put them in the relevant bags. Numbers they considered are 7, 100, 9, 11, minus 3, 0, minus 1 by 4, 5, 1, 3 by 7, minus 1, 0.12, minus 13 by 17, 13.222, and so on, 19, minus 5 by 3, 213 by 4, minus 69 by 1, 22 by 7, 5.6 bar. Natural numbers n 7, 100, 9, 11, 5, 1, 19. Whole numbers w equals to 7, 100, 9, 11, 0, 5, 1, 19. Integers z 7, 100, 9, 11, minus 3, 0, 5, 1, minus 1, 19. Rational numbers q 7, 100, 9, 11, minus 3, 0, minus 1 by 4, 5, 1, 3 by 7, minus 1, 0.12, minus 13 by 17, 13.222, so on, 19, minus 5 by 3, 213 by 4, minus 69 by 1, 22 by 7, 5.6. Rational numbers on number line. Let us remind how to represent the rational numbers on number line. Take the fraction 3 by 4 and represent it pictorially as well as on number line. Solution. We know that 3 by 4 means selecting 3 parts from a total of 4 parts of a single unit. In 3 by 4 fraction, 3 is numerator and 4 is denominator. Pictorially, 3 by 4 is represented as representation of 3 by 4 on number line. Example. Are the following statements true? Give reasons for your answer with an example. 1. Every rational number is an integer. 2. Every integer is a rational number. 3. 0 is a rational number. Solution. Take the first statement. Every rational number is an integer. Integers include only positive whole numbers and negative whole numbers and 0. But rational numbers include positive numbers, negative numbers, fractions, decimals. For example, 7 by 8 is a rational number but an integer. Hence, every rational number is not an integer. Every integer is a rational number. True. Because every integer can be written in the form of p by q, where p, q are integers and q is not equal to 0. For example, -2 can be written as -2 equals to -2 by 1 equals to -4 by 2. Which are rational numbers? 0 is a rational number. True, because 0 can be expressed as 0 by 13, 0 by 1, 0 by -2. P by Q from where P, Q belongs to Z and Q is not equal to 0. Example, find two rational numbers between 3 and 4 by mean method. Solution. Method 1. We know that rational number lie between two rational numbers A and B is A plus B by 2. Given rational numbers are 3 and 4. So, the rational number lie between 3 and 4 is 3 plus 4 by 2 equals to 7 by 2, which is between 3 and 4, and 3 is less than 7 by 2 is less than 4. If we repeat the above process, we can find many more rational numbers between 3 and 7 by 2. The rational number lie between 3 and 7 by 2 is 3 plus 7 by 2 by 2 equals to 6 plus 7 by 2 divided by 2 by 1 equals to 13 by 2 into 1 by 2 equals to 13 by 4, which lie between 3 and 7 by 2. Thus, 3 is less than 13 by 4 is less than 7 by 2 is less than 4. Method 2. This is another method in finding two rational numbers in single step. Here, we want two rational numbers between 3 and 4. Hence, we write 3 and 4 as rational numbers, that is, P by Q from with denominator 2 plus 1 equals to 3. 3 equals to 3 by 1 equals to 6 by 2 equals to 9 by 3 and 4 equals to 4 by 1 equals to 8 by 2, 12 by 3. Take the rational numbers which are having denominator 3. Therefore, 9 by 3 and 12 by 3 are rational numbers which are having denominators 3. So, the numbers between 9 by 3 and 12 by 3 are 10 by 3, 11 by 3, which lie between 3 and 4. 3 equals to 9 by 3 is less than 10 by 3 is less than 11 by 3 is less than 12 by 3 equals to 4. For two rational numbers between 3 and 4, we take denominator as 2 plus 1 equals to 3. If we want 5 rational numbers between 3 and 4, then we have to take denominator as 5 plus 1 equals to 6. Therefore, 3 equals to 3 by 1 equals to 6 by 2 equals to 9 by 3 equals to 12 by 4 equals to 15 by 5 equals to 18 by 6. 4 equals to 4 by 1 equals to 8 by 2 equals to 12 by 3 equals to 16 by 4 equals to 20 by 5 equals to 24 by 6. Therefore, 3 equals to 18 by 6 is less than 19 by 6 is less than 20 by 6 is less than 21 by 6 is less than 22 by 6 is less than 23 by 6 is less than 24 by 6 equals to 4. By observing this example, we might have realized that there are infinite rational numbers between any two rational numbers. Example, express 7 by 16, 10 by 3 in decimal form. Solution: 0.4375 Therefore, 7 by 16 equals to 0.4375 is a terminating decimal. 10 by 3. Therefore, 10 by 3 equals to 3.3333 and so on equals to 3.3 bar is a non-terminating recurring decimal. Example, express 3.28 in the form of p by q, where p and q are integers and q is not equal to 0. Solution: 3.28 can be written as 3.28 equals to 328 by 100 equals to 328 divided by 2 by 100 divided by 2 equals to 164 by 50 equals to 164 divided by 2 by 50 divided by 2 equals to 82 by 25. Therefore, 3.28 equals to 82 by 35. Example, express 1.62 bar in the form of p by q, where p, q are integers and q is not equal to 0. Solution: 1.62 bar equals to 1.62626262 so on. Let us take x equals to 1.626262. Let this be equation 1. Here, periodicity is 2, so multiply 100 on both sides of equation 1. 100 into x equals to 100 into 1.626262 so on. 100x equals to 162.626262 so on. Let this be equation 2. Subtract 1 from 2. 100x equals to 162.626262. X equals to 1.626262. 99x equals to 161.000000. 99x equals to 161. X equals to 161 by 99. But x equals to 1.6262, so on. Therefore, 1.626262, so on, equals to 161.99. 1.62 bar equals to 161 by 99. Irrational numbers. The decimal numbers which are non-terminating and non-recurring are called irrational numbers. They cannot be represented in P by Q form. Irrational numbers are denoted by letter S. The square root of any prime number is irrational only. There are infinite irrational numbers between two rational numbers. Let us take a prime number and find the square root. Find the value of root 2 by long division method. Solution. Follow the steps below. Step 1. After 2, place decimal points. Step 2. After decimal points, write zeros. Step 3. Group 0 pairs and put a bar over them. Step 4. Then after, follow the method of find the square root of the perfect square. Therefore, root 2 equals to 1.4142135, so on. If we observe the value of root 2, it is neither terminating nor repeating. We cannot represent this value using bar. This type of numbers are called irrational numbers. Similarly, root 3 equals to 1.732080756896, so on. Root 5 equals to 2.360697974998, so on. Representing irrational numbers on number line. We know the representation of rational numbers on the number line. We can use a point to represent a rational number between rational numbers. Like that, we can point as many rational numbers between rational numbers. Now, let us discuss how to represent irrational numbers on the number line. Square root of 2 on number line. Locate root 2 on number line. Solution. Draw the number line and construct a square on number line. With each side of 1 unit in length, let 0 be the point on the number line. And starting from 0, draw square 0, A, B, C. By Pythagoras theorem, 0 b square equals to 0 a square plus ab square equals to 1 square plus 1 square equals to 1 plus 1 equals to 2. 0 b equals to root 2. Using a compass with 0 and radius as 0b, draw an arc on the number line to the right of 0. It will intersect at a point K on the number line. Now, point K corresponds to root 2 on the number line. Square root of 3 on number line. Locate root 3 on number line. Solution. Draw a number line and construct a square on number line. from a point 0 and name the square as 0, A, B, C. Each side of 1 unit length, join 0, B and construct a line BD perpendicular to 0, B, which is also of length 1 unit. Now join 0, B according to Pythagoras theorem. In triangle 0, B, D, 0 D square equals to 0 B square plus BD square equals to root 2 square plus 1 square equals to 2 plus 1 equals to 3. 0 D equals to root 3. With center at 0 and radius as 0 D, draw an arc on the right of 0. It intersects at a point M. The point M corresponds to the value of root 3 on number line. Note: we can point many irrational numbers on the number line. In the same way, we can locate root n for any positive integers n after root n minus 1 has been located. Know about pi. Pi is defined as the ratio of the circumference C of the circle to its diameter d. That is, pi equals to C by d. As pi is in the form of ratio, this seems to the contraction of fact that pi is irrational. There does not exist a common unit to measure that allow us to measure circumference C and diameter d. If you measure accurately, then at least either circumference or diameter is irrational. So, pi is regarded as irrational. The Greek mathematician Archimedes was the first to compute the value of pi. He showed that the value of pi lie between 3.14085 and 3.14287. Aryabhatta, 476 to 550 AD, the great Indian mathematician and astronomer, found the value of pi correctly to 4 decimal places: 3.1416. Before pi has been computed to over 1.24 trillion decimal places, pi equals to 3.141592658932338, so on. The decimal expansion of pi is non-terminating, non-recurring. So, pi is an irrational number. Note that we often take 22 by 7 as approximate value of pi, but pi is not equal to 22 by 7. We celebrate March 14th as Pi Day. Since it is March 3rd, that is month and date 14, which is representing the value of pi equals to 3.14. Albert Einstein was born on March 14, 1879. Real numbers. All rational numbers can be written in the form p by q, where p and q are integers and q is not equal to 0. There are also other numbers that cannot be written in the form p by q, where p, q are integers are called irrational numbers. The collection of rational numbers and irrational numbers are called real numbers. Real numbers are denoted by R. Every real number is represented by a unique point on the number line. Also, every point on the number line represents a unique real number. So, we call this as real number line. Examples: -5, -6, √21, -2, 0, 22/7, √9, √2, 12.513, pi are examples of real numbers. Finding irrational numbers between numbers. Till now, we find the rational between the given rational numbers. Let us find the irrational numbers between given rational numbers or irrational numbers. Find any two irrational numbers between 1/5 and 2/7. Solution: convert the given two numbers into decimal form. 1/5. Therefore, decimal form of 1/5 equals to 0.2, 2/7. Therefore, 2/7 equals to 0.285714228. This is non-terminating and recurring number. Hence, we can write the number as 2/7 equals to 0.285714228. 1/5 equals to 0.20, which is a rational number. 2/7 equals to 0.2857142, which is non-terminating and recurring number. So, examples of two such irrational numbers are 0.201201201111, so on. 0.2411411114. 0.232161711819. 0.267812147512. Finding an irrational number between two rational numbers. If a and b are two positive rational numbers such that AB, product of a and b, is not a perfect square of irrational numbers, then root AB is an irrational number lying between A and B. Example, find an irrational number between 3 and 4. Solution. Given rational numbers are 3, 4. Product of 3 and 4 equals to 3 into 4 equals to 12, which is not a perfect square. Therefore, irrational number between 3 and 4 equals to square root of 3 into 4, root 3 into root 4 equals to root 3 into root 2 square equals to root 3 into 2 equals to 2 root 3. An irrational number between 3 and 4 is 2 root 3. Examine whether the following numbers are rational or irrational. 3 plus root 3 plus 3 minus root 3. Solution. Remove the brackets and add them. 3 plus root 3 plus 3 minus root 3 equals to 3 plus root 3 plus 3 minus root 3 equals to 3 plus 3 equals to 6, which is a rational number. 3 plus root 3, 3 minus root 3. Solution. We know that a plus b, a minus b equals to a square minus b square. Therefore, 3 plus root 3, 3 minus root 3 equals to 3 square minus root 3 square equals to 9 minus 3 equals to 6, which is a rational number. 10 by 2 root 5. Solution. 10 by 2 root 5 multiply with root 5 in numerator and denominator. 10 by 2 root 5 equals to 10 by 2 root 5 into root 5 by root 5 equals to 10 into root 5 by 2 root 5 into root 5. We know that root 5 into root 5 equals to 5 equals to 10 into root 5 by 2 into 5 equals to 10 into root 5 by 10. 10 by 2 root 5 equals to root 5, which is an irrational number. Root 2 plus 2 whole square. Solution. Root 2 plus 2 whole square. This is in the form of a plus b whole square. Therefore, a plus b whole square equals to a square plus 2ab plus b square. Root 2 plus 2 whole square equals to root 2 whole square plus 2 into root 2 into 2 plus 2 square equals to 2 plus 4 into root 2 plus 4. Root 2 plus 2 whole square equals to 6 plus 4 root 2, which is an irrational number. Representation of real numbers on the number line through successive magnification. We have seen that any real number has a decimal expansion. Now, let us know how to represent terminating decimal on the number line. If we magnify the scale, we will see small divisions present on it. If we see the scale through magnifying glass, then the portion of scale from 3 to 4 is as follows. If we magnify, it can be further divided between 3.1 and 3.2 as 3.11, 3.12, 3.13, 3.14, 3.15, 3.16, 3.17, 3.18, 3.19. Example to represent terminating decimal on the number line. Represent 2.776 on number line. Number line is as follows. Given terminating decimal number is 2.776 lies between 2 and 3. By seeing closely, the portion between 2 and 3 will be as follows. Now, 2.776 lies between 2.7 and 2.8. Imagine the portion between 2.7 and 2.8 are divided into 10 equal parts. We have to divide furtherly the portion between 2.77 and 2.78 between 2.776 lies between them. The markings on the number line are 2.771, 2.772, 2.773, so on, 2.779, 2.780. 2.776 is the sixth mark in these subdivisions on the above number line. This process of visualization of presentation of numbers on the number line through a magnifying glass. As the process of successive magnification, visualize the position of a real number with a non-terminating recurring decimal expansion on the number line. Let us see how we will mark the point of a real number which is non-terminating recurring decimal on the number line by the process of successive magnification. Discuss with an example below. Example. Visualize the representation of 3.58 bar on the number line through successive magnification up to 4 decimal places. Solution. We should proceed the same process of the real number with terminating decimal. Here it is given the non-terminating decimal, but we have to visualize up to 4 digits after decimal point. So, the number we have to mark on the number line is 3.5888. 3.5888 means it lies between 3.5 and 3.6, so represent it on the number line. Again, if we magnify and visualize the portion between 3.5 and 3.6 by dividing it into 10 equal parts, it will be as follows. 3.5888 lies between 3.58 and 3.59. Again, we have to repeat the process. Magnify and visualize the portion between 3.58 and 3.59 by dividing it into 10 equal parts. So, the marks on the number line are 3.581, 3.582, 3.583, 3.589. Here, we can say that 3.5888 lies between 3.588 and 3.589. Divide the portion between 3.588 and 3.589 into 10 equal parts. Operations on real numbers. We know the operations that are performed by the rational numbers and laws such as commutative, associative, and distributive laws are satisfied or not. Let us see the operations and laws that are performed by irrational numbers. Observe the following examples. Root 3 plus minus root 3 equals to 0. Here, 0 is a rational number. Root 5 minus root 5 equals to 0. 0 is a rational number. Root 2 into root 2 equals to 2. 2 is a rational number. Root 7 by root 7 equals to 1. 1 is a rational number. By the above examples, it is clear that the sum, difference, quotients or divisions and multiplication of irrational numbers need not be irrational numbers. So, irrational numbers are not closed with respect to addition, subtraction, multiplication and division. Properties related to square roots. Let a and b be positive real numbers. Then root ab equals to root a, root b. Root a by b equals to root a by root b. If b is not equal to 0. Root a plus root b into root a minus root b equals to a minus b. A plus root b into a minus root b equals to a square minus b. Root a plus root b into root c plus root d equals to root ac plus root ad plus root bc plus root bd. Root a plus root b whole square equals to a plus 2 root ab plus b. Example. Check whether the following are irrational numbers or not. 5 root 2, 5 by root 2, 21 plus root 3, pi plus 3. Solution. We know that root 2 equals to 1.414 so on. Root 3 equals to 1.732 so on. Pi equals to 3.1415 so on. 5 root 2 equals to 5 into 1.414 so on equals to 7.070 and so on is non-terminating and non-recurring number. So, 5 root 2 is an irrational number. 5 by root 2 equals to 5 by root 2 into root 2 by root 2 equals to 5 root 2 divided by root 2 into root 2 equals to 5 into 1.414 so on divided by 2 equals to 7.070 so on divided by 2. 5 by root 2 equals to 3.535 so on, which is non-terminating and non-recurring decimal. Therefore, 5 by root 2 is an irrational number. 21 plus root 3. 21 plus root 3 equals to 21 plus 1.732 so on equals to 22.732 so on, which is non-terminating and non-recurring decimal. Therefore, 21 plus root 3 is an irrational number. Pi plus 3. Pi plus 3 equals to 3.1415 so on plus 3 equals to 6.1415 so on, which is non-terminating and non-recurring decimal. Therefore, pi plus 3 is an irrational number. Note: if q is rational and s is irrational numbers, then q plus s, q minus s, q into s and q divided by s is not equal to 0 are irrational numbers. Simplify the following. Add 5 root 3 and 7 root 3 plus 3 root 7. Subtract 5 root 3 plus 7 root 5 from 3 root 5 minus 7 root 3. Multiply 3 plus root 3 and 2 plus root 2. Solution. Add 5 root 3 and 7 root 3 plus 3 root 7. Rule. Add the like terms means we have to add the numbers which are having the same numbers in the roots, like root 2, root 3, root 5 equals to 5 root 3 plus 7 root 3 plus 3 root 7. Add root 3 terms and root 7 terms separately. 12 root 3 plus 3 root 7. Therefore, 5 root 3 plus 7 root 3 plus 3 root 7 equals to 12 root 3 plus 3 root 7. Subtract 5 root 3 plus 7 root 5 from 3 root 5 minus 7 root 3. Subtract like terms only. 3 root 5 minus 7 root 3 minus 5 root 3 plus 7 root 5 equals to 3 root 5 minus 7 root 3 minus 5 root 3 minus 7 root 5 equals to 3 root 5 minus 7 root 5 minus 7 root 3 minus 5 root 3 equals to minus 4 root 5 minus 12 root 3 equals to minus 4 root 5 plus 12 root 3. Multiply 3 plus root 3 and 2 plus root 2. 3 plus root 3 into 2 plus root 2 equals to 3 into 2 plus 3 root 2 plus 2 root 3 plus root 3 into root 2 equals to 6 plus 3 root 2 plus 2 root 3 plus root 3 into 2. Root a into root b equals to root ab. Therefore, 3 plus root 3, 2 plus root 2 equals to 6 plus 3 root 2 plus 2 root 3 plus root 6. Rationalizing the denominator. We cannot locate the irrational numbers on the number line when the number is in denominator. For example, if we try to locate 1 by root 2 on the number line, we have to find the value of 1 by root 2. As we know, root 2 equals to 1.414213, so on, which is neither terminating nor repeating. We cannot divide 1 with the value of root 2. So, we have to change the denominator into rational form. To rationalize the denominator of 1 by root 2, multiply the numerator and denominator of 1 by root 2 by root 2. We get 1 by root 2 equals to 1 by root 2 into root 2 by root 2 equals to root 2 by root 2 into root 2. Root a into root a equals to a. 1 by root 2 equals to root 2 by 2. It is said that 1 by root 2 is half of root 2. Now, we can mark 1 by root 2 on number line. It lies exactly between 0 and root 2. Rationalizing factor. We know that root 2 into root 2 equals to 2. Hence, we can say root 2 is rationalizing factor of root 2. Definition. If the product of two irrational numbers is a rational number, then each of the two is the rationalizing factor of the other. The rationalizing factor of a given irrational number is not unique. It is convenient to use the simplest of all rationalizing factors of given irrational number. Example: root 2 into root 8 equals to root 16 equals to root 4 square. Root 2 into root 8 equals to 4. Hence, the product of root 2 and root 8 is 4, which is a rational number. Hence, root 2 and root 8 are rationalizing factors of each other. Note: root 2 is the simplest rationalizing factor of root 2. Example: rationalize the denominator of 1 by 4 plus root 5. Solution. We know that a plus root b, a minus root b equals to a square minus b, which is a rational number. So, multiply numerator and denominator of 1 by 4 plus root 5 by 4 minus root 5. 4 minus root 5 is rationalizing factor of 4 plus root 5. Therefore, 1 by 4 plus root 5 equals to 1 by 4 plus root 5 into 4 minus root 5 by 4 minus root 5 equals to 4 minus root 5 by 4 plus root 5 into 4 minus root 5 equals to 4 minus root 5 by 4 square minus root 5 whole square equals to 4 minus root 5 by 16 minus 5 equals to 4 minus root 5 by 11. Example: 3 root 5 minus root 7 by 3 root 3 plus root 2. Solution. We know that root a plus root b into root a minus root b equals to a minus b. which is a rational number. Multiply numerator and denominator of 3 root 5 minus root 7 by 3 root 3 plus root 2 by 3 root 3 minus root 2. Therefore, 3 root 5 minus root 7 by 3 root 3 plus root 2 into 3 root 3 minus root 2 by 3 root 3 minus root 2 equals to 3 root 5 minus root 7 into 3 root 3 minus root 2 by 3 root 3 plus root 2 into 3 root 3 minus root 2 equals to 3 root 5 into 3 root 3 minus 3 root 5 into root 2 minus root 7 into 3 root 3 plus root 7 into root 2 divided by 3 root 3 whole square minus root 2 whole square. Since a plus b into a minus b equals to a square minus b square equals to 9 into root 5 into 3 minus 3 into root 5 into 2 minus 3 into root 7 into 3 plus root 7 into 2 divided by 3 square into 3 minus 2. Root a into root b equals to root ab equals to 9 root 15 minus 3 root 10 minus 3 root 21 plus root 14 divided by 9 into 3 minus 2 equals to 9 root 15 minus 3 root 10 minus 3 root 21 plus root 14 divided by 27 minus 2. 9 root 15 minus 3 root 10 minus 3 root 21 plus root 14 divided by 25. Law of exponents for real numbers. Let us recall the law of exponents. A to the power m into a to the power n equals to a to the power m plus n. A to the power of m whole to the power of n equals to a to the power of mn. A to the power m by a to the power n equals to a to the power of m minus n. If m is greater than n, 1 if m is equal to n, 1 by a to the power of n minus m if m is less than n. A to the power of m, b to the power of m equals to a into b whole to the power of m. 1 by a to the power of n equals to a to the power of minus n. A to the power of 0 equals to 1. Here a, b, m, n are integers and a is not equal to 0, b is not equal to 0. A is called base and m, n are the exponents. Examples: 7 cube into 7 to the power of minus 3. Solution: 7 cube into 7 to the power of minus 3 is in the form of a to the power of m into a to the power of n. Therefore, a to the power of m into a to the power of n equals to a to the power of m plus n. 7 cube into 7 to the power of minus 3 equals to 7 to the power of 3 plus minus 3 equals to 7 to the power of 3 minus 3 equals to 7 to the power of 0. Therefore, 8 to the power of 0 equals to 1 equals to 7 to the power of 0 equals to 1. Therefore, 7 cube into 7 to the power of minus 3 equals to 1. 2 to the power of 3 whole to the power of minus 7. Solution: 2 to the power of 3 whole to the power of minus 7 is in the form of a to the power of m whole to the power of n. Therefore, a to the power of m whole to the power of n equals to a to the power of mn. 2 to the power of 3 whole to the power of minus 7 equals to 2 to the power of 3 into minus 7 equals to 2 to the power of minus 21. Therefore, 1 by a to the power of n equals to a to the power of minus n equals to 1 by 2 to the power of 21. 23 to the power of minus 7 divided by 23 to the power of 4. Solution: 23 to the power of minus 7 by 23 to the power of 4 is in the form of a to the power of m by a to the power of n. Therefore, a to the power of m by a to the power of n equals to a to the power of m minus n. 23 to the power of minus 7 by 23 to the power of 4 equals to 23 to the power of minus 7 minus 4 equals to 23 to the power of minus 11. 7 to the power of minus 13 into 3 to the power of minus 13. Solution: 7 to the power of minus 13 into 3 to the power of minus 13 is in the form of a to the power of m into b to the power of m. Therefore, a to the power of m into b to the power of m equals to a into b whole to the power of m. Therefore, 7 to the power of minus 13 into 3 to the power of minus 13 equals to 7 into 3 whole to the power of minus 13 equals to 21 to the power of minus 13. We learned the concept of bases and exponents for rational numbers. We need to expand the knowledge for the laws of exponents to bases of positive real numbers and to the exponents as rational numbers. Let us discuss these laws and also what is nth root of the real number. If b to the power of n equals to a for some positive real numbers b, then b is called nth root of a, and we write n to the root a equals to b. Observe the following. If 2 to the power of 2 equals to 4, then square root of 4 equals to 2. Square root of 4 equals to 4 to the power of 1 by 2 equals to 2 to the power of 2 whole to the power of 1 by 2 equals to 2. 2 to the power of 3 equals to 8. Then cube root 8 equals to 2. Cube root 8 equals to 8 to the power of 1 by 3 equals to 2 to the power of 3 whole to the power of 1 by 3 equals to 2. 2 to the power of 4 equals to 16. Then 4th root 16 equals to 2. 4th root 16 equals to 16 whole to the power of 1 by 4 equals to 2 to the power of 4 whole to the power of 1 by 4 equals to 2. 2 to the power of 5 equals to 32. Then 5th root 32 equals to 2. 5th root 32 equals to 32 whole to the power of 1 by 5 equals to 2 to the power of 5 whole to the power of 1 by 5 equals to 2. 2 to the power of 6 equals to 64. Then 6th root 64 equals to 2. 6th root 64 equals to 64 whole to the power of 1 by 6 equals to 2 to the power of 6 whole to the power of 1 by 6 equals to 2. Similarly, if a to the power of n equals to b, then nth root b equals to a, nth root b equals to b whole to the power of 1 by n equals to a to the power of n whole to the power of 1 by n equals to a to the power of n by n equals to a to the power of 1 equals to a. Note: square root of 4 is not equal to 2 into root 4. It is square root of 4. Similarly, cube root 4 is not equal to 3 into root 4. It is cube root of 4. Laws of exponents to the basis of positive real numbers and rational exponents. Let a is greater than 0 be a real number and p, q be rational numbers, then we have a to the power of p into a to the power of q equals to a to the power of p plus q. A to the power of p to the power of q equals to a to the power of p into q. A to the power of p by a to the power of q equals to a to the power of p minus q. A to the power of p into b to the power of p equals to a into b to the power of p. N root a equals to a to the power of 1 by n. Examples: 2 to the power of 2 by 3 into 2 to the power of 5 by 3. Solution: this is the form a to the power of m into a to the power of n equals to a to the power of m plus n. Therefore, 2 to the power of 2 by 3 into 2 to the power of 5 by 3 equals to 2 to the power of 2 by 3 plus 5 by 3 equals to 2 to the power of 2 plus 5 by 3 equals to 2 to the power of 7 by 3. 5 to the power of 1 by 7 to the power of 4. Solution: this is of the form a to the power of m to the power of n equals to a to the power of mn. Therefore, 5 to the power of 1 by 7 to the power of 4 equals to 5 to the power of 1 by 7 into 4 equals to 5 to the power of 4 by 7. 3 to the power of 1 by 3 by 3 to the power of 1 by 5. Solution: this is of the form a to the power of m by a to the power of n equals to a to the power of m minus n. 3 to the power of 1 by 3 by 3 to the power of 1 by 5 equals to 3 to the power of 1 by 3 minus 1 by 5 equals to 3 to the power of 5 minus 3 by 15 equals to 3 to the power of 2 by 15. 7 to the power of 1 by 17 into 11 to the power of 1 by 17. Solution. This is of the form a to the power of m into b to the power of m equals to a into b to the power of m. Therefore, 7 to the power of 1 by 17 into 11 to the power of 1 by 17 equals to 7 into 11 to the power of 1 by 17 equals to 77 to the power of 1 by 17. Calculate the roots. Simplify 625 to the power of 1 by 4. Solution. We can write 625 as follows. 625 equals to 25 into 25 equals to 5 into 5 into 5 into 5 equals to 5 to the power of 4. Therefore, 625 to the power of 1 by 4 equals to 5 to the power of 4 to the power of 1 by 4 equals to 5 to the power of 4 by 4 equals to 5 to the power of 1 equals to 5. Therefore, 625 to the power of 1 by 4 equals to 5. Simplify 16 to the power of 3 by 2. We have to write 16 to the power of 3 by 2 as 16 to the power of 1 by 2 to the power of 3. 16 to the power of 3 by 2 equals to 4 square to the power of 1 by 2 to the power of 3 equals to 4 to the power of 2 by 2 to the power of 3 equals to 4 to the power of 3 equals to 4 into 4 into 4 equals to 16 into 4. Therefore, 16 to the power of 3 by 2 equals to 64. Sued. If n is a positive integer greater than 1 and a is a positive rational number but not nth power of any rational number, then n root a or a to the power of 1 by n is called sued of nth order. In general, we say the positive nth root of a is called sued or a radical. Here, a is called radicand. N root is called radical sign and n is called degree of radical. Examples for sued: root 2, root 3, 3 root 9, and so on, etc. Forms of sued. They are exponential form a to the power of 1 by n, radical form n root a. Consider a real number root 7. It can also be written as 7 to the power of 1 by 2. Since 7 is not a square of any rational number, root 7 is a sued. Consider 3 root 8. 8 is cube root of 2. So, 3 root 8 is not a sued. Consider the real number root 2. It is written as 2 to the power of 1 by 2 to the power of 1 by 2 equals to 2 to the power of 1 by 2 into 1 by 2.